All right, in the next test, we're going to discuss convergence of series similar to 1 over n squared. I already told you before that the series converges, but so far we haven't proved it. So before formulating how this next test is going to look like, let's try to apply the test from the previous section to 1 over n squared and see what will happen. So the easiest test was a test for divergence, where you take the function 1 over n squared in this case, and you take a limit when n goes to infinity. If the limit is 0, then you cannot really say anything. If the limit is not 0, then it means that the series does not converge. So in this case, limit of 1 over n squared actually is 0, so the divergence test really is not going to tell you anything. Number 2, if I try to apply root and a ratio test, then we can observe that 1 over n squared is a ratio of two polynomials, 1 and n squared. And I mentioned during the last lecture that whenever you have a rational function of n, then both root and ratio test will be inconclusive, because the appropriate limits that you'll have to take will all be equal to 1. So divergence test doesn't work here. Root and ratio tests do not work. The last hope is a comparison test. And at this point, our library of functions library of series for which we know convergence involves only 1 over n, as well as a geometric series. So clearly 1 over n squared probably should be compared to 1 over n. It would be difficult to compare it to a geometric series. And the problem with 1 over n is that it gives you a harmonic series which diverges, so the sum of a series is infinity. And at the same time, 1 over n is greater or equal than 1 over n squared for all n, so that means that the sum of 1 over n squared should be less or equal than sum of 1 over n, and sum of 1 over n is infinity, so that means that the series 1 over n squared should add up either to a finite number or to infinity, so we don't really know if the series converges or not. So that means that the comparison test really is not going to be of any use at this point, and we have to come up with a different test. So this is something called the integral test, and I'm not going to prove it. One clear reason is that it should involve integrals, and we have not discussed integration yet. So what I'm going to do, I'm going to illustrate it by using, again, the example of a series 1 over n squared, and then we'll formulate how this test is going to look like and apply it. So if I have a series of 1 over n squared, if I let f of x to be 1 over x squared, then the term of my series, 1 over n squared, is actually a value of f at n. So let's forget about the series for a moment and just look at this function on the interval from 0 to infinity. In fact, we can even look at the interval from 1 to infinity. So the graph of 1 over x squared should look basically like the graph of 1 over x. Is going to be f of x is going to be diverging when x gets close to 0. The graph goes to infinity. You have a vertical asymptote. And when x goes to infinity, 1 over x squared would go to 0. So you also have a horizontal asymptote at infinity, y equal to 0. Now, x squared is always increasing, so 1 over x squared will be always decreasing. So we have a monotone decreasing function like this. And actually, if we compare it to 1 over x squared, if x is larger than 1, then x squared is greater than x, then 1 over x squared is going to be less than 1 over x. And when x is between 0 and 1, then x is going to be bigger than x squared, so 1 over x squared is going to be smaller than 1 over x. Is going to be 1 over x squared is going to be larger than 1 over x. So on the interval from 0 to 1, 1 over x squared is above 1 over x, and on the interval from 1 to infinity is below 1 over x. So for one thing, then, that the area under the graph of 1 over x squared on the interval from 1 to infinity should be smaller than the area under the graph of 1 over x. Okay, so with that in mind, now how do we compute the exact area under the graph of 1 over x squared? You need to take an improper integral from 1 to infinity like this. Remember that the improper integral means that because the upper limit is infinity, you have to take an integral up to t and then let t go to infinity. So anyhow, exact area under the graph of f of x is given by this integral. And now if we recall the definition of a definite integral, the way it was introduced, the way we introduced it, we use the concept of a Riemann sum. And a particular example of a Riemann sum is something that I've drawn on this picture here in front of you. So we take an interval from 1 to infinity. We subdivide it into intervals of a length 1. So you have an interval from 1 to 2, 2 to 3, 3 to 4, and so on. And above each of these intervals, I can construct a rectangle. So notice that in this case, I chose rectangles to have a height that is equal to the value of the function at the leftmost point of a given interval, right? So at 1, it's given, the first integral is equal to the value of the function of 1. Notice that things here are not at the right scale, of course. So then, same for the second rectangle, same for the third rectangle, and so on. If I design the rectangles like this, then clearly the area under the graph on the interval from 1 to 2 is going to be smaller than the area of the rectangle. The same thing for the interval from 2 to 3, from 3 to 4, and so on. So if I take all areas of these integrals, all areas of these rectangles, and I add them up all the way up to infinity, I'm going to get a number which is larger than the area under the graph. Now, what is the height of the first rectangle? It's 1 over 1 squared. Second one is 1 over 2 squared. Third is 1 over 3 squared, and so on. And the bases of all rectangles are equal to 1. So then if I add up areas of all rectangles, I'm going to get a summation like this. And it's easy to check that what this is, it's actually the sum of a series of 1 over n squared. And so what we conclude from this picture is that the sum of a series 1 over n squared must be larger than the integral from 1 to infinity of 1 over x squared. All right, so now let's do the second construction. And the second construction is going to be almost the same as the first one, except that on each interval I'm going to use the right endpoint of the interval to calculate the height of the corresponding rectangle. So the first rectangle will have a height 1 over 2 squared, right? Because that's a right endpoint of the interval from 1 to 2. Right endpoint of the interval from 2 to 3 is 3. So the height of the second rectangle is 1/3 squared. And you continue like that forever. And then if I add the areas of all of these rectangles, what I would see is that I underestimated the area under the graph. So sum of areas of all rectangles must be smaller than the area under the graph from 1 to infinity. So then what is the total area of rectangles? It's 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. Remember that bases of all rectangles have a length 1. And that is the same series, infinite series, 1 over n squared, except that the first element of the series is 1 over 2 squared, so that means that my summation starts at 2. Okay, and so then what we conclude from this is that the sum of a series starting from 2 is less now than the area under the graph from 1 to infinity. Well, the only thing that I'm missing here from, if I compare to the full series starting from 1 to infinity, is 1 over 1 squared in the beginning, which is 1. So if I add 1 to both sides of this equation, then I'm adding essentially the first element of the series, so I can start my summation from 1. And I have to add 1 to both sides, so I'll have to add 1 to the integral on the right side as well. And so from this, we conclude the following, that the integral of 1 over x squared from 1 to infinity is less than the series, right? That's from the first picture. And from the second picture, 1 plus integral from 1 to infinity is greater than the sum of the series. Now what this means is that if the integral is going to give me a finite number, that means that the sum of a series should be a finite number. And if the integral is infinity, then the series is larger than the integral, so that means that the series would also add up to infinity. So then the conclusion is that the series and the integral from 1 to infinity will either both converge at the same time or both diverge at the same time. And so we can use the integral to determine whether the series converges or not. And so in this case, what I need to do is I need to compute an integral of 1 over x squared from 1 to infinity. So as I said, this is an improper integral. So I take a limit as t goes to infinity of the integral from 1 to t. Integral of x to the minus 2 is minus x to the minus 1. From 1 to t, that's 1 minus 1 over t. If t goes to infinity, 1 minus 1 over t goes to 1. So that means that the integral is equal to 1. Which means that then the series, sum of a series, is less than 1 plus 1, 2, and greater than 1. So then we know that the series converges. But not only it converges, its value also can be estimated. Its value now is going to lie somewhere between 1 and 2. Okay, and so now I'm going to formulate the integral test. Let's suppose that I have a function f of x, which is decreasing on the interval from 1 to infinity, number 1. Number 2, the limit of this function as x goes to infinity is equal to 0. So then we make the following conclusion, that the series of f of n is going to converge as long as the integral from 1 to infinity of f of x converges as well. So in order for the integral test to be applicable, that function f of x that determines terms in your series must be decreasing on the interval from 1 to infinity, and its limit as x goes to 0, x goes to infinity must be equal to 0. So in particular, that means that the function f of x must be positive. All right, and so now let's do a couple of examples of integral test. So we now know that 1 over n squared series like that converges. Series of 1 over n diverges. What about the series of 1 over n to the power p, where p is any constant number? A series like that, by the way, is called a p-series. First, let's look at the case when p is less or equal than 0. If p is less or equal than 0, and I look at my 1 over n to the p, I can always write 1 over n to the p as n to the minus p. And if p is negative or non-positive, then minus p should be non-negative, right? So minus p is either 0 or a positive number. So then if I take a limit of n to the minus p when as n goes to infinity, not p, sorry, then what I see is that if p is 0, so n to the 0 is equal to 1, then the limit is 1. And if p is less than 0, minus p is positive, then n to the p goes to infinity. So in neither case, 0 or a negative number, p is 0 or p negative, 1 over n to the p goes to 0, and if it doesn't go to 0, then the series fails the test for divergence, and so the series must diverge when p is negative. All right, so then an alternative is that p is positive. So then let's check if we can apply the integral test. For 1 over n to the p, your relevant function of x is 1 over x to the p, and 1 over x to the p clearly is decreasing on the interval from 1 to infinity. And we can in particular determine that by taking a derivative. Again, this is something that we have not introduced yet rigorously, but you already know what the derivative is and how to compute it. So this would be a good way to determine if your function is decreasing. So if I take the derivative of x to the minus p, I'm going to get something like that, x to the minus p minus 1 for x positive, for x greater than 1, in fact, is a positive number. Minus p, when p is positive, is negative, so this number is less than 0. So f of x is a decreasing function. And clearly, as x goes to infinity, 1 over x to the p will go to 0. So then the integral test, we satisfy two conditions for the integral test. Integral test applies, and so we need to compute the integral from 1 to infinity of 1 over x to the p. And we can do that in the same way as we worked out the example of 1 over x squared, with one small caveat. So integral from 1 to infinity of 1 over x to the p, right, that's improper integral. So again, I'm writing it as a limit when t goes to infinity of this integral. Now, the integral of x to the minus p, of course, is x to the power 1 minus p over 1 minus p, but it only works if p is not equal to 1, so at this stage I'm going to assume that p is not equal to 1. Then you plug in t. 1 over 1 minus p is a constant factor that goes outside of a limit. So we need to take a limit of something like this. Limit of 1, of course, is always 1. What about t to the power 1 minus p? If p is less than 1, then we're raising t to a positive power. So as t goes to infinity, t to the positive power will go to infinity. So if p is less than 1, the limit is infinity, so the integral diverges. But if p is greater than 1, then 1 minus p is a negative number, so we're raising t to a negative power. And as t goes to infinity, t to the negative power will go to 0. So this term goes to 0. Then we just have minus 1 as a limit times 1 over 1 minus p. So we get 1 over p minus 1. So the integral converges if p is greater than 1, diverges if p is less than 1. What about p equal to 1? Well, p equal to 1, you get a series of 1. So we're working with 1 over n to the p. If p is equal to 1, that's just 1 over n. That's a harmonic series. So we know already that it diverges. So then the conclusion is that the series of 1 over n to the p series, is going to diverge for p, any p which is less or equal than 1, and it will converge if p is greater than 1. So you see that the integral test immediately allows us to determine the convergence of a fairly large class of series. And one more test. Let's look at a series like this. Does it converge or not? And at this point, we are allowed to use any test that you would wish. So if the easiest test to use, again, is the divergence test. What is the limit of this expression as n goes to infinity? It's 0, right? So divergence test is going to be inconclusive. Comparison test might work or might not. What are you going to compare it with? You can try to compare it to 1 over n. 1 over n is larger than 1 over n over ln of n squared, and 1 over n diverges. So if a larger series diverges, that gives you no information. Or you can try to compare it to 1 over n squared, but then you can show that 1 over n squared is going to be smaller than this. So again, if I have a smaller series that converges, this doesn't tell me anything about the larger series. So a comparison test is not going to work so well here. And I'm not going to do it, but you can check root and the ratio test. In fact, I will encourage you to check it yourself. If you try to use a root and the ratio test, then once again, both of those tests will come up inconclusive. So as much as you don't like it, you will have to use the integral test in this case, and if it is possible. So the relevant function is going to be f of x equal to 1 over x ln x squared, or x ln x squared to the power minus 1. Again, I need to show, in order for me to be able to use the integral test, I need to show that f of x is monotone decreasing and its limit is 0. To prove that it is monotone decreasing, I need to take a derivative. You take a derivative, you end up with an expression like that by using the chain rule and the product rule. So what about the sign of this expression? In this case, a series is actually evaluated from 2 to infinity, right? Because I couldn't start at 1 because the ln of 1 is equal to 0. So that means that I have to show that this function f of x is decreasing on the interval from 2 to infinity. From 2 to infinity. And if x is greater than 1, then ln of x is positive. So then this term is positive, this term is positive. Squared and fourth power are both positive, and there is a minus sign in front. So that means that the derivative is less than 0, and so that if x is greater or equal than 2. And that means, in fact, it is strictly less than 0. And that means that f is strictly decreasing on the interval from 2 to infinity. So the first condition for the integral test is satisfied, and then if we take a limit of the function 1 over x times ln of x squared, then clearly ln of x squared when x is greater than 2 is a number which is eventually going to be greater than 1 as x gets bigger. So that means that the limit, that means that this sequence, not sequence, but this function is less than 1 over x, right? Because you're dividing by something greater than 1. And the limit of 1 over x when x goes to infinity is 0. And then this is a positive number. So that means that by using the squeeze theorem, we see that this limit actually is equal to 0. So both conditions of the integral test are satisfied. Therefore, it applies. And the only thing it is left to do is to evaluate the integral. So I need to evaluate the integral again now. I'm starting at 2, so integral is evaluated starting from 2. And clearly what I can use here is a substitution. Sorry, u equal to ln of x, because dx over x is a differential of ln of x. You do a substitution, you end up with something like this. Again, this is an improper integral, but I'm going to just fake it a little bit. I'm not going to write the limit, I'm just going to mentally assume that u in this expression will go to infinity. So to evaluate minus 1 over u at infinity, I need to take minus 1 over u and let u go to infinity. If I do that, then minus 1 over u will go to 0. And then I have to subtract the circle thing evaluated ln of 2. Subtracting a negative number, I get a positive number, so this is 1 over ln of 2. So the integral converges, and therefore the original series would also converge by the integral test. All right, and the next time we're going to introduce an additional test, something called the alternating series test, that you have seen already in calculus. Yeah, you saw in calculus a long time ago.